Okay. Well, good morning, everybody. My name is Henry Garcia. I'm part of the Pizza Donuts group, and I joined the fellowship in September, so a couple of months ago. And I would like to present to you this paper called Big Self-Supervised Models are Strong Semi-Supervised Learners. The motivation behind is we have a lot of different supervised models, and we want to increase the accuracy of the training process. However, having supervised data is expensive. So what I'm going to show you here is a method that combines both unsupervised pre-training and supervised fine-tuning. And there's different components of this method. I think the first component is what is called simCLR version 1, and I'm going to explain to you how it works. Then I'm going to go deeper into the details of the method, how exactly the author of the papers approached the problem. We're going to look at the results just to explore how they were getting results compared to previous methodologies, and then we'll have some discussions about related work and the broader impact on society. So as I said, labeled data is limited and is also expensive. So it takes a long time to collect good quality data and basically label this data. Is not easy, and it can be quite challenging. And so the question is how we can make better use of all the unlabeled data that we have, and use a few label examples to come up with reasonable models that can help us predict. In this case, they apply the methodology for classification. So basically, the answer they propose is to use unsupervised pre-training and followed by fine-tuning. And I will go more into the details now. One thing we should cover before we go into the details of the method is what is called simCLR version 1. And the paper that I'm describing to you is actually two parts. The first part, they describe simCLR, and they compare that to other methods, and they came up with this graph where they show that the simCLR approach for different models is actually increases the accuracy close to the level of supervised methodologies. So I think they were very excited during this first version of the methodology, because they managed to reach almost 80% accuracy with this unsupervised or semi-supervised methodology. So how does it work? Before going into the method of the paper, I would like to explain a bit briefly the simCLR version 1. And basically the way it works is we make use of the images, and we make use of different augmentations for the images. And then, as is shown in this graph, we use these augmented images and we pass them through an encoder. And that encoder, usually deep neural network like ResNet, for example, is going to give us a representation of that image in a different space. And then we take those representations and pass it through a multi-layer PEP central layer. In this case, they use a one hidden layer. and they created another representation in a different space called Z. And in this space called Z, they basically want to use a loss where basically they have the ability to group things that are similar together. And then they have also the ability to separate things that are different. So as you can see here on the left side is a very nice diagram where they show how two different images, the dog and the chair, they go through this process of augmentation, then encoder, then the multi-layer perceptron, and then finally we separate it using the loss. Now the loss function is a similarity function based on the dot product of these vectors, of these representations. And as you can see on the right, basically is defined as the exponential of the similarity between the two images from the same image divided by the similarity of the image that is different. In this case, the image of the chair, for example. And they do this. They calculate this loss as defined here over a batch, and then they use a batch to train the network, and they do so until they manage to reach the lowest accuracy as possible. Do you have any questions so far? Hello? I can hear. I can hear something in the background.
Abdul, can you mute your microphone, please?
Do you have any UI design development?
Hello?
No, I mean, you have done all the existing ones. Well, except the calendar. Yeah, okay.
Right.
You have integrated the services API. I'm not sure if there are services that I can use that I don't know that I can use. Because I'm around this one here, and he was really busy yesterday.
Guys, can you please mute? Guys, can you please mute yourself? Okay, well, I'll try to continue then. So now that we, hello, sorry, there is a lot of noise in the background.
Yeah, Abdul, can you hear me? Could you please mute your microphone? Hello, Abdul.
Hello? Okay, now it's better now. Okay, that's better. Okay, so I was explaining about the methodology for simCLR B1. Now I'm gonna go more into the details of the method of this paper in a specific. And the methodology is divided into three main steps. First, we have an unsupervised step where we use unlabeled data and we train an agnostic convolutional neural networks. And we also have a multi-layer perceptron on top of this that is actually acting as a nonlinear transformation of the representations of the image. Then the second stage is a supervised fine-tuning with a small portion of labeled data. And then finally, we have a third stage where we have what is called a self-training of distillation, where we try to use, we try to build a neural network that is more task-specific to the problem we want to do. And I will show you some details of one of these for each of these stages. So in the first stage is you have to conduct self-supervised pre-training with simCLR B2. So this stage is basically what I already explained to you for simCLR B1. But there are three differences that they improve the methodology. The main difference are that they make the encoder deeper. Instead of using ResNet 50, for example, they are using ResNet 152. The other main difference is in the projection head at the top of the encoder. It's now deeper. Instead of one hidden layer, they have two hidden layers or 3 layers in total. And lastly, they also incorporated this momentum construct, which basically is an encoder that help you bring these negative examples for the images in an organized way, and it's based on a moving average. So if you have these images, for example, x0 key, x1, x2, then it will transform them into another representation, k0, k1, by using a moving average, and then this the representations on the queue will go into the normal process of calculating the loss. So that's the first step. Then the second step, as I mentioned, they use supervised fine-tuning, and for this, in this case, they use a subset or the small label set that they have, and they fine-tune the network on a classic classification methodology, like that we're probably familiar with, except that instead of throwing away the projection head completely, in this case they fine-tune from the first layer of the multi-layer pepsintron, which is basically what they are fine-tuning is the ResNet architecture plus some fully connected layers. And this is the key difference with simCLR V1. In simCLR V1, they throw away the MLP completely. And then lastly, in the last stage is what they call the self-training knowledge distillation via unlabeled examples. And in this stage, basically how it works is once they have the fine-tuned big network, this is what they call the teacher network. And because this network is already trained, once you pass an image, you will have, in the case that we have a classification process, you will have an output that is a probability of each of the classes. And then in that way, we can classify the image. But what you do, you pass the same image through a smaller neural network, and then you calculate the probability of the classes, and you will probably get something that is different, of course, to what the teacher network is giving you. And so what you do is you take the output of the two, and then you calculate a loss, and you use that loss to train the student network or the small network. And this has several advantages. It improves the classification process in itself, but it also gives you a smaller neural network, which could be beneficial if you want to deploy the application for mobile applications, for example, where you need when you don't have a lot of computer power. So that's it in a nutshell, how the method works. We have the self-supervised pre-training using a second version of simCLR. Then they fine-tune that network using a small set of images. And then finally, they create this self-knowledge and distillation to have a smaller neural network and a better classification. So then they go into the details of the paper of exactly how they apply this, and they apply this method to ImageNet, and they were dealing with 1.228 million images, and basically using 1% or 10% of the labels as label data. They use the LAR optimizers. They use a batch size of 4096 and 800 epochs. And they increase the learning rate linearly until they reach 5% of the data, and finally decrease the learning rate with cosine decay. As augmentations, they use the simple augmentations that are proposed by the simCLR version 1, which is random crop, color distortion, and Gaussian blur. And one thing I would like to highlight here is the importance of having a big batch size. As you can see in this case, they're doing more, a batch size that's greater than 4,000. And also the amount of epochs they have to take. In this case, they are talking about in the order of 800s. So this methodology relies heavily on having a big batch size and on having many training epochs. And obviously they were very thoughtful about all the experiments that we run. So we can see in this table, they run different networks, ResNet 50, 101, 152, with different widths and different, and that results into different models that have a different number of parameters. And then they did the fine tuning for 1% with the label data, fine tuning with 10% of the label data. And then they also try fine tuning with 100% of the data. And then for comparison purposes, they apply a linear classifier on the network. So they can compare that to the fine tune methodology. And also, of course, they compare the results to a full supervised approach. And then these are basically the plots from this graph, from this table. And as you can see, they came to the conclusion that bigger models are more label efficient. And by that, I mean, if you look at the plots, we have three plots. We have the plots for supervised learning, and we have the plot for semi-supervised learning, the approach that I just described. And the third one is basically a zoom image of the second one. But as you can see, in the case of supervised learning, increasing the model improves very little as you make the model bigger and bigger. The increase in accuracy is not that great, and that happens for the 1% of the labels, which is in blue, and 10% of the label, which is in red, and 100% of the label that is in green. However, when you look at the results for a semi-supervised method that I just described, and then you can see that actually when you have fewer labels, which is 1% here in blue, and you increase the model, you're actually increasing the accuracy considerably, and a lot more than in the case where you use supervised learning. And the same holds true when you have 10% of the data, but as you go into 100% of the data, then the increase in the accuracy is reduces again. So basically, something that is counterintuitive is that the bigger model we have for less fraction of the labeled data, the better. And this is against the common conception that the bigger models will actually overfit. Then they also study the impact of the projection head. And here they show the results for our ResNet 50 network, where they try different number of layers in the multi-layer PET centron projection head. And you can see that they have results for 1% of the labels, 10% of the labels, and then 100. And as you can see, for the cases where we have 1% and 10%, as you increase the number of layers in the projection head, the accuracy tends to increase. But it remains flat when we have 100% of the label data. Also, they try in the bottom row, they tried different layers. fine-tuning from different layers in the same multi-layer perceptron. And as you can see, they get the best results when they fine-tune from the first layer of the multi-layer perceptron in both, when we have 1 or 10% of the data. If we have 100% of the data, however, the best thing to do is not to use a projection head. And finally, they say that actually doing the distillation improves the semi-supervised learning. And you can see in this plot, we have the accuracy for the cases where they have simCLR fine-tuned only in blue, simCLR self-distilled in red, and self-CLR distilled in green, and then the case where we have supervised in black. So as you can see, as we increase the number, of parameters, and as we use distill options, which is in green, we tend to have better accuracies as compared to the case where when we don't use the distill option in the methodology. Then they compare the results to different related work. In this case, how do you use different unlabeled data to model a specific task, or how do you use unlabeled data to model task agnostic problems. And then they compare to their way or to their methodology, where they basically use both. And as you can see in the comparisons, they show that their values tend to be higher than previous methodologies applied for different problems and different data sets. So in conclusion, this simple framework for semi-supervised learning is a new and novel approach. Similar approaches have been approached in NLP, and now they are making their way into computer vision. Bigger models can produce larger improvements when you have few labels. And task agnostically learned general representation can be distilled into a more specialized and compact network using unlabeled examples, which gives you both two benefits. The network will be smaller and the classification will be better. And finally, they talk about the broader impact of these methodologies. They claim this can be used for medical applications, and this can increase, for example, crop yields in agriculture. But they also warn against potential bad applications like hard-phone surveillance systems, or also reducing the industry of labeling services. And that's it. That's the end of my presentation.